Hi, I'm Mike Seaman with Eta One Power, and today I'll show you how to design a current mode buck converter in Eta Designer. Here's a standard voltage mode buck converter. The output voltage is fed through an error amplifier into the PWM modulator, which then provides PWM pulses to the power stage MOSFETs. The pulse width of the MOSFETs is controlled to obtain the desired output voltage. Voltage mode converters can be difficult to control. First, they typically require a more complex PID controller, not just a PI controller. Adjusting the compensator can be more involved, and the controller will often be sensitive to parameter variation. A voltage mode buck will also respond slowly to transients and has no inherent current limit to protect the converter in overcurrent conditions. Next, let's look at the current mode buck converter. We can measure the inductor current and feed it into the PWM modulator. We can use any number of methods to measure the current. For example, a Hall effect sensor, shunt plus amplifier, DCR sensing, or measuring the current through the high side switch. Instead of controlling the duty cycle, the error amplifier output is now used to set the cycle-by-cycle current limit for the topology. Let's look at the waveforms for the peak current mode controller. The switch is turned on at the beginning of each period and turned off when the inductor current reaches the command current. The command current is output of the error amplifier and is controlled to achieve the desired output voltage. With a current mode buck converter, a simple compensator, such as a PI controller, can be used. A faster transient response can also be obtained. One challenge with current mode control is that when the duty cycle exceeds 50%, subharmonic oscillation can occur. There will be a stable, steady-state oscillation in the current waveform as shown here. This can lead to a number of undesired consequences and should be avoided. The subharmonic oscillation can be eliminated by adding slope compensation to the controller. Here, we subtract a periodic ramp from the command signal that is used to compare with the sensed current. The ramp amplitude is selected to stabilize the current waveform and avoid subharmonic oscillation. A ramp slope of V out divided by 2L will stabilize the buck converter at all duty cycles. Next, let's use Eta Designer to implement and simulate a current mode buck converter. We'll start by using the new converter wizard to create a new voltage mode buck converter. We'll use this as a starting spot for our current mode buck converter and then make the necessary changes. We'll define a minimum input voltage of 9 volts, a typical value of 24 volts, and a maximum of 36 volts. The output voltage of this converter is 3.3 volts with an output current from 0 to 10 amps. Next, select a buck converter and then choose a switching frequency of 500 kHz. So here's our starting point. We'll convert it to a current mode buck converter by adding an element to sense the inductor current. In this case, we'll use a current-controlled voltage source for simplicity. Next, we'll wire up the sense element and reconnect the disconnected wires. We'll then adjust the sense gain of the controlled source. As the maximum output current is 10 amps, we'll choose a gain of 0.1 volts per amp for a maximum sense voltage of 1 volt at our 10 amp load. Now, let's modify the controller by double-clicking on it. We will first add an input pin for our sensed current signal. Next, we will add the slope compensation ramp. We'll name the ramp iSlope. We want a slope of V out over 2L to ensure no subharmonic oscillation. For this converter, this will be a value of 1.65 amps per microsecond or 0.165 volts per microsecond when scaled by the sensor gain. We'll write that as 0.165 megavolts per second. We'll use a limit of 1 volt and we'll set the ramp to reset every rising edge of the high side PWM waveform. Now, let's define the PWM waveforms for this converter. We already have constraints to set the dead time between the high side PWM and the low side PWM to 20 nanoseconds. We also have a period constraint of 2 microseconds set on the following edge of the low side PWM waveform. Now we need to modify the constraint on the falling edge of the high side PWM to implement peak current mode control. First, we'll set the constraint to an input compare. We'll set the falling edge to occur when the sensed current is greater than the output of our compensator, in this case V loop. We'll then subtract our slope compensation ramp from the output of this compensator. We'll use greater than here instead of rises above to ensure a level-based comparison rather than an edge trigger. A level-based comparison will ensure that the pulse width is minimal when the current level already exceeds the command when the switch turns on. We also want to add a couple other constraints. First, we add a constraint to ensure that the switch stays on for at least 50 nanoseconds to blank out the current spike during the turn-on transient. This delay is referenced to the rising edge of the high side PWM waveform. We then add another constraint to set the maximum pulse width. We use a logical OR here to ensure that either the current limit or the maximum pulse width will turn off the high side switch. We'll set the maximum pulse width to be 1.8 microseconds after the rising edge of the high side PWM to ensure a maximum duty cycle of 90%. Now that we have the structure of the controller defined, we can wire the current sense to the controller and run an initial simulation of the circuit. While we see that the circuit is stable, the transient response is incredibly slow. You might notice that we haven't yet adjusted the compensator, so we need to do that now. First, we'll double-click on the V-loop compensation filter and then examine the response. You see that the crossover frequency is at 1.7 kilohertz, which is very slow. We'll start by choosing a simple PI filter, which is good for a current mode converter. The first thing we'll do is adjust the DC gain quite a bit to 500,000, for example. This will give us a crossover of 86 kilohertz and a phase margin of 50 degrees. However, you'll notice that we have a slow zero of 30 kiloradians per second, which will yield a slow tail to our transient response. We'll fix that by setting a zero of 400K and a pole of 10 times that, or 4 meg. We'll see that our bandwidth has fallen a bit to 18 kilohertz, so we'll boost our gain again to get a crossover of 60 kilohertz, and we'll see we also, at that frequency, we have a phase margin of 48 degrees. And finally, we'll adjust the output range of our compensator. A converter has a maximum steady state output current of 10 amps, which is a sense value of 1 volt. Allowing some headroom for transient response and our slope compensation ramp, we'll set a maximum of 2 volts or 20 amps. Now we'll click OK and take a look at the transient response. Now you see that we have a fast transient response with little overshoot. It's really easy to then adjust the compensator to fine-tune the response to your liking. I hope you've enjoyed this video and have learned how to use Eta Designer to analyze your power converter projects. Please check us out at etadesigner.com to download a trial version and to view more videos like this one. Thanks.